Okay. And so is that the only one? You. Okay. All right. So welcome, scholars. Let me see. So we are at the top of week 10. Just as a reminder, I think week 12, we have exam 3 over chapter 2. So today we're just continuing chapter 2. You know, same rules apply. This is remote asynchronous. And, you know, if you have questions or if you need to get my attention, the best way is to unmute yourself to just get my attention. You can use the chat, but I'll check the chat periodically. And again, I will check attendance again around the 15-minute mark for anybody that's late. Now today, with this section, I mean, it's dry. Like, I'm not gonna lie. Like, because I like to work examples, but there's a lot of like terminology here. It's a lot of like concepts. You know, so you just have to bear with me and do the best you can. So we're continuing chapter 2 with polynomial and rational functions. And so we're working on section 2.2, polynomial functions. And so some objectives we have, we want to learn the properties of graphs of polynomial functions, determine the end behavior of polynomial functions, find the zeros of a polynomial function by factoring, identify the relationship between degrees, real zeros, and turning points, and graph polynomial functions. I think with this class, the main thing, you want to make sure that you're making your way through the material that's on Pearson. Keep in mind with our assignments on Pearson that we get unlimited attempts. You can go back and work on any old assignments, including exams, and improve your score up to 90%, right? If you are trying to improve your overall score, my recommendation would be to prioritize the exams as they're worth nearly 80% of your overall grade. And then the other thing is that you want to make sure that you're following the instructions of Dr. Lamar. She facilitates the lab, and basically you can see your lab grade on Blackboard. I think it's live. So all I do is I go to calculate the final grades. Whatever grade I see that she has there for you, I'm going to take that and say times 0.1 and add it to your overall grade. So that way it'll count for 10% of your overall grade. Okay. So let's keep going here. So we have some definitions. We have that a polynomial function of degree n. Let me grab this guy. So a polynomial function of degree n is a function of this form, right? Where n is a non-negative integer. So these are all non-negative integers. And the coefficients a sub n, all of these guys, these are real numbers with the leading coefficient not equal to 0. So a polynomial, all it is a finite sum of monomials, right? A monomial is some real number times a variable x to a non-negative integer power, right? Again, a monomial is some real number times a variable x to a non-negative integer power. Once you identify a monomial, then a polynomial is just a finite sum of monomials, right? Finite sum, okay? Finite meaning it's like it's limited. It doesn't go on forever. So the term a sub n x to the n is called the leading term. The number a sub n is called the leading coefficient. And a sub 0 or a naught is called the constant term. It's just a number. The constant function f of x equal to a, where a is not 0, can be written in the form of f of x equals a times x to the power of 0 is a polynomial of degree 0. So the degree of a polynomial is the highest power on any variable. If you have some function equal to some non-zero real number, then we say that's a polynomial of degree 0. But not to be confused with the 0 function, f of x equal to 0, this has no degree because it's not unique. You can write this as equals 0, but that's equal to 0 times x squared, which is equal to 0 times x cubed, which is equal to 0 times x to the 1 million, right? So because you can't write this in one unique way, we say that it has no degree assigned to it. And then polynomials of degree 3, 4, and 5 are called cubic is 3, quartic is 4, and quintic is 5, right? So I'll check Zoom in just about 9 minutes. 9 minutes. Did you first your own? Okay, let's keep going. So this expression where basically we have a polynomial, Again, that's a polynomial. Then the function f, defined by f of x equal to that polynomial. Again, we call that a polynomial function. And the equation where we have that polynomial equal to 0 is called a polynomial equation, right? So again, a polynomial is just a finite sum of monomials. Finite sum of monomials. A polynomial function is basically f of x equal to that polynomial. And then a polynomial equation is where you have the polynomial equal to 0. Okay. Oh yeah, I forgot I can do that. Single page. I totally forgot about that. Okay. So then some common properties of polynomial functions. The domain of a polynomial function is a set of all reals. So once you identify a function as polynomial, again, one property of polynomial functions is that their domain is all reals. The graph of a polynomial is a continuous curve, right? So by continuous, we mean that we can start at any point on the graph and we can start tracing the graph and we can get to any other point without picking our pen up off the curve, right? So there are no holes or gaps or breaks. So the example on the left is an example of a polynomial function. But on the right-hand side, suppose we started at this point and we started tracing. In order to get to the points on the further right, we had to pick up our pen to get over that gap, right? So because this one has a hole or a gap or a break, this one cannot be the graph of a polynomial. So again, this slide is saying the graph of a polynomial curve is a continuous unbroken curve, no holes or gaps or breaks. Another property of the graph of a polynomial is that it has smooth curves, right? It has smooth curves, no sharp corners or edges or anything like that. So the example on the right is an example of something that's not a polynomial because we have a sharp corner or edge. Okay. So then here we're asked to state which functions are polynomial functions. For each polynomial function, find the degree, the leading term, and the leading coefficient. Okay. Anybody feel, let me see. If you had to guess, could you guess the first one is either a polynomial, yes or no? Right? Do you think that part A is a polynomial, yes or no? Right. So again, remember, polynomial is a finite sum of monomials. So here's one monomial, here's another one, and here's the third one, right? So we have three different monomials we're adding. So this is a trinomial. Notice that each coefficient is a real number, and the variables are raised to non-negative integer powers, right? So part A is an example of a polynomial function. For each polynomial function, find the degree. So the degree is the highest power on any variable. So the degree here is going to be 4. And the leading term is going to be 5x to the 4. And the leading coefficient is going to be 5. The leading term is the term that has the highest power, right? Sometimes they write these guys out of order. So it is a good idea to put it in descending power order, and it makes it easier to work. So if you had to guess on part B, would you guess part B is a polynomial, yea or nay? Right? So I would say that without this guy here, then I would say, yeah, it is a polynomial. But one thing we just said a slide or two ago, we said that the domain of a polynomial is all reals. This domain is restricted between 1 and 5. So this guy cannot be a polynomial, right? So this isn't a polynomial. So I think we have a type version of what we just said, okay? So f of x is a polynomial function. The degree is 4, the leading term is 5x to the 4, the leading coefficient is 5. G of x is not a polynomial because its domain is not all reals, okay? So a function of this form is called a power function of degree n, where a is a non-zero real number and n is a positive integer. So a power function is basically f of x equal to a monomial. Again, where the leading coefficient is a real number, right here, a non-zero real number, and n is a positive integer, okay? So just it's equal to a monomial. Let me see the time. We got a solid 4 minutes before I check it. So then we have power functions of an even degree, okay? So let f of x equal this monomial or be this power function. Then if n is even, then, if we consider negative x to the power of an even, to an even power, If we have an even number of negatives multiplied, then the result is going to be positive. So negative x to the power of n, where n is even, gives us this positive x to the n. So then basically what's going on is we're looking at f of negative x, and we're finishing with f of x. That's the definition of a function being even. All right, when we start with f of negative x and we finish with f of x, that means the function is even. Even means we have y-axis symmetry, right? So you can fold it on the y-axis, and the left-hand side would be a mirror image of the right. And the graph of y equals x to the n, again, when n is even, is similar to the graph of y equals x squared. Where y equals x squared is a parabola, it's a U-shaped curve. So then whenever we're considering a power function of even degree, the graph is going to be similar to the graph of y equals x squared. It's like basically, you know, the tail ends go off in the same direction, right? That's kind of what that's getting at. Let's take a little over 2 minutes, and then I'll check it again. I'm just kind of waiting to give people time to kind of get into the waiting room, because otherwise I would constantly be checking the attendance, and you know, I already had this urge to check it, but it would really disrupt the rhythm and the flow. So then we want to consider power functions of odd degree. So consider the power function where n is odd. Then if we consider negative x to the power of n, if you multiply an odd number of negatives, you can finish with negative times x to the n, right? So that means that we're starting with f of negative x and we're finished with negative times f of x. That's the definition of a function being odd. That's the definition of a function being odd, right? So when a function is odd, that means we have symmetry with respect to the origin, okay? And the graph of the power function when n is odd is going to be similar to the graph of y equals x cubed. In other words, our tail ends are going to go in opposite directions, okay? And origin symmetry, again, one of the ways to articulate that, whenever you have a point x comma y on your graph, you also have the point negative x comma negative y. So all of your points are going to be symmetric and equidistant from the origin. All right, it's going to pass through the origin, and you're going to have points that mirror each other centered around the origin, moving around like that or whatever. Okay. So then we have this end behavior of polynomial functions. So we have this case one. This is missing something where it should say when n is even. Copy. Okay. So we're going to look at the end behavior. Let me see the time. I'll get to these. So we're looking at the end behavior of polynomial functions, and there's going to be 4 cases. The first 2 cases pertain to when n is even. So the way I remember this, if we have a positive leading coefficient, that tells me that my graph is going to go up to the right. Positive leading coefficient, here, let's do this again. A positive leading coefficient, my graph goes up to the right. If the degree of the polynomial is even, I know the other side does the exact same. So for me, even in this context means exact same. So then if we can consider when the leading coefficient is positive, meaning it goes up to the right, we can also consider where the leading coefficient is negative, right? And it's still even in this case. So if the leading coefficient is negative, that means we should go down to the right. Even means the exact same, so the other side is going to go down as well. It's going to do the same thing. Let me check the zone really quickly. All right. Okay. All right. Let's go back here. I'll check this again in a moment. Okay. Right. So we went through the 2 cases when n was even. So then there are 2 cases when n is odd. Okay. So here, we're still going back to the leading coefficient is positive, but now we want to consider when n is odd. Copy. So just like we said a moment ago, when the leading coefficient is positive, that means our graph goes up to the right. When n is odd, that means the other side does the opposite, so it goes down to the left. Okay. And then the final case, case 4, is when the leading coefficient is negative and n is odd. So a negative leading coefficient means it's going to go down to the right. N is odd is up to the left. Okay. So we just went through 4 cases of the end behavior of a polynomial function. This was based on, for the polynomial. Actually, this is based on the power function, right? But that's fine for now. Okay. All right. So let's take a look at this one. So given this polynomial function of degree 3, show that this polynomial is approximately equal to the power function 2x to the power of 3 when the absolute value of x is very large, right? So this is just kind of like a story. You shouldn't really be doing a lot of this, but this is just kind of trying to put a little bit of these concepts into context, right? So if we start with our polynomial, and we have this 2x cubed plus 5x squared minus 7x plus 11, right? We want to consider, let's start by factoring out x cubed from all the terms. So if we factor out x cubed from each term, the first term we're going to be left with 2. Then we're going to be left with 5 over x. Then we're going to be left with a negative 7 over x squared. And lastly, we're going to be left with 11 over x cubed. Okay. All right. And you can, we could check, because if we were to distribute back, x cubed times 2 is going to be 2x cubed. If you distribute there, you're going to get 5x squared, so on and so on. You can show that when you distribute back, it works out. So then we want to consider, let me see, so let the absolute value of x basically go to infinity. So then as the absolute value of x goes to infinity, then this term, this 5 over x, this negative 7 over x squared, and this 11 over x cubed, these guys get closer and closer to, this goes to 0. They get closer and closer to 0. As that denominator is bigger and bigger and bigger, and the numerator is fixed, it's not changing. So then those fractions get smaller and smaller and smaller the further absolute value of x gets closer to infinity, right? So then if we factor that in, then we're going to have that p of x is approximately x cubed times 2 plus 0 plus 0 plus 0, which is approximately 2x cubed. Just put a box, right? So that's what we were showing. We were showing that starting with p of x, as the absolute value of x goes off to infinity, then this polynomial behaves similar to this power function, right? So again, you're not really going to be doing it this way. This is just providing some context on how we're able to go from those 4 cases for the power function to these 4 cases for the polynomial, right? And so because of this thing here, basically we can extend those 4 cases from the power function, we can extend it, where it's essentially the same thing to the power function, to the polynomial function, all right? So then that basically brings us to this, where we have this leading term test, right? We have this leading term test. So then given a polynomial function where the leading coefficient is not 0, again, this is a polynomial function, the leading term is a sub n x at the end. The behavior of the graph as x tends to infinity or negative infinity is similar to one of the following 4 graphs and is described as shown in each case. The middle portion of each graph indicated by the dashed lines is not determined by this test, right? So again, this is an extension of the power function. So let me see, can I paste? Okay. Let's get rid of this. N is even. Right here. So these first two cases are when n is even. And it's kind of a repeat of what we did just a moment ago. So with the leading coefficient being positive, that means the graph goes up to the right. Because the degree of the polynomial is even, then that means the other side does the exact same thing. It goes up as well, right? So that was the first case. The second case, copy. So the leading coefficient is positive. We can also consider the leading coefficient being negative, right? A negative leading coefficient means the graph falls to the right. Because the degree of the polynomial is even, the other side does the exact same thing. It falls as well. Again, this test doesn't tell us anything about the middle, all right? We don't know anything about the middle. It doesn't give us any information there, but it tells us about what happens as x tends to positive infinity or negative infinity when considering a polynomial, okay? Let's see, case 3. So then case 3, in this one, our name is gonna be odd. Okay. Let me copy. Okay. So because the leading coefficient is positive, that means our graph is going to go up to the right. But because the degree of the polynomial is odd, that means the other side does the opposite. Okay. Up to the right, down to the left. Okay. And then the fourth case, let me copy this. Let me make sure I get a copy. The fourth case, because our leading coefficient is negative, our graph is going to fall as we go to the right. And because the degree of the polynomial is odd, the other side is going to do the opposite and go up. Okay. So the leading term test is an extension of those 4 power rules that we had earlier. And again, it gives us no information about the middle of the graph, but it tells us about the long-term behavior of the graph. Okay. All right, let me check something. Cool. Okay, so, since you guys aren't here, I'm just going to piggyback off of my other recordings. You can just watch one of theirs because it's the same information. And I'm not going to sit here and talk to myself. So on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. See you Wednesday. Take care.